In this section, we're going to take a look at solving homogeneous linear equations, specifically those with constant coefficients. Now, we've seen a couple of techniques, the separation of variables and use of integrating factors to solve these kinds of problems. However, under certain conditions, there is another, simpler way of thinking about these. And in conjunction with the reduction of order, we'll be able to solve second-order homogeneous equations, believe it or not, mostly with just using algebra. Okay? So consider the following. Consider ay1 plus by equals 0. Very simple differential equation, first order. Okay. Well, here I can always write this by isolating my y prime. That's going to be y prime equals negative by divided by a. So I guess I'll write this negative b over ay. Okay. Here, the a and the b are, again, constant coefficients. Okay, well, this is just some number, right? Negative number over number is just a number. So here I can write this as just y prime equals a constant times y. But we know what that is. We've known this since before this course. We've known this since, what, Cal 1. What's the only function who is, when you take its derivative, nothing changes except maybe the constant? Well, there's two of them, right? There's y equals 0, which is what we call the trivial solution, right? 0 prime is equal to any number times 0. That is definitely true. But the exponential function does that. Y equals e to the kx. Because after all, if this is e to the kx, and I take its derivative, I get e to the kx again. Oh, except times the extra k thanks to the chain rule. You can try that, right? Plug that in, it'll work. So what that means is that both y and y prime are just going to be multiples of the exponential function. Right? Thus, y and y prime are all going to be just multiples of the exponential function. You say, okay, so what? Well, if that's the case, I can write y as some number. Well, actually, I guess y itself would be an exponential function, so I could write that as e to the mx, and then y prime would be me to the mx, something like that. And yeah, that would just be by taking the derivative. The derivative of the exponential is itself, but then the chain rule says to multiply by the derivative of mx, which would just be m. Okay, giving our problem the form of, okay, so I've got an a up front, and then my y prime is m e to the mx, plus, then over here I've got a b up front, and then my y is e to the mx equals to 0. But notice, since both of these are multiples of e to the mx, that means e to the mx is a constant. Is a common factor. I don't know why I said a constant. E to the mx is certainly not a constant. It's an exponential function. It's a common factor. I can factor it out. That's e to the mx. I know why it is. It's almost noon. It's lunchtime. So here I've got e to the mx, which I can factor out, giving me am plus b equals to 0. You say, okay, so what? Well, notice that this can never equal to 0. All right, the exponential function is never 0. It approaches 0 asymptotically, but it never actually reaches 0. Okay, so since this is never 0, then this, in order to solve this equation, this is the one that's got to be 0. Right? This is never 0. So it's got to be this one. So the problem reduces down to just am plus b equals 0, which is very easy to solve. This is a linear problem. Not a linear differential equation, but just a regular linear equation, the kind you learned in basic algebra. Here you can subtract the b to the other side, divide by a, and you get m equals negative b over a. Oh, but that m is the m in our solution. So our solution is e to the minus b over a times x. But that's just a single solution. Oh, but don't forget, whenever you find a solution to a homogeneous linear equation, then any multiple of that is also a solution. The linear combination of all of the fundamental solutions are going to form the general solution. This is the first order problem though, right? Yeah, first order. Oh, so the fundamental solution set only has one element. Oh, so that's it. This is our fundamental solution set. It is a solution, but it's also the fundamental solution set. It only needs one element because it's a first order problem. Thus, our general solution is y equals C1. I guess I could just say C because there's only one of them, but whatever. C1 e to the minus b over ax. And there we go. But notice this problem here is nothing more than a simple polynomial. Notice one other thing. It looks like our original problem did. Coefficient of a, here you have a first derivative, here you have a first power, plus b, here you don't have any derivative, and here you don't have any power, equals 0. So did I have to go through all of this to get to this point, or could I have just said, oh, that looks like this, so I can just jump there? Yeah, that's exactly what we can do. Our next definition formalizes that statement. The auxiliary function, the auxiliary equation. This is also sometimes called the characteristic equation. They're both interchangeable. However, I personally, when I was a student, I learned it as the characteristic equation, so I tend to use that one more often, but they are interchangeable. So here I'm going to say the auxiliary equation. Characteristic equation means the same thing for our purposes. Of a homogeneous linear ODE. Of the type a sub n times the nth derivative of y plus a sub n minus 1 times the n minus first derivative of y plus dot 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 plus a sub 1 y prime plus a sub 0 y equals 0. The auxiliary equation of this, the characteristic equation of this is, you're going to take the coefficients exactly as they are. The number of derivatives you've taken is going to translate to the power on a polynomial function, on a polynomial equation. So here this will be a n x to the power of n. Not n derivatives, but just the power. Just like over here, first derivative became first power. Plus a sub n minus 1 x to the power n minus 1 plus dot 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 plus a sub 1 y first derivative becomes x first power. We don't usually write first power. We usually would just write x plus a sub 0. No derivative means no power on your variable. And when there's no power on your variable, usually you don't even bother writing the variable. You can write x to the 0 here, but most people don't. Is equal to 0. This is called our characteristic equation, also called our auxiliary equation. So as a simple example of this, let's say the characteristic equation of, let's say 5y double prime plus 3y prime minus 6y equals 0. The characteristic equation would be 5x squared plus 3x minus 6 equals 0. It's a polynomial equation. Number of derivatives translates to power on the variable. No derivative means no power. This is a very common mistake. People will want to write that as an x, but no. No derivative, no power, no variable. Okay. Once you have this is a polynomial equation. You could solve. There's lots of ways of solving this. I could use a quadratic formula. I could factor. I could complete the square. I could use the rational zeros theorem. There's a bunch of ways I've learned to solve polynomial equations. I learned a bunch of ways in algebra, right? So when we solve this, depending on what solutions we get from this, we will know what kind of solutions our original ODE has. So here, note the kinds of solutions of this characteristic equation tell us the kinds of solutions of the ODE. Okay. So here, let's go ahead and look at a technique that lays out exactly what the kinds of solutions we can expect are and what they each mean for our general solution. So technique. All right. So here we're going to be solving, and for now we're going to stick with second order, although this does work for higher order, but for now we're gonna just stick to second degree, right? No, you know what? We can do higher ones. But anyway, the technique talks about second order ones here. We'll talk about what happens to higher ones in the examples. Okay? So here we're looking at solving second order specifically. Homogeneous linear ODEs with real constant coefficients. Real constant coefficients. Okay, so our first step here, we're going to go ahead and write the characteristic polynomial equation. Second of all, we're going to solve that polynomial equation to find zeros. If you think back to algebra, every quadratic equation has two solutions. Those two solutions can fall into one of three categories. They're either both real and different from each other, they're both real and they're the same, or they're both complex. So we're going to have three different cases here. Solve the characteristic equation to find solutions M1 and M2. These are not the solutions to the ODE, these are the solutions to just the polynomial equation. Okay, so now step number 3, separate into cases. Separate into cases, and there's going to be 3 different cases. If your two solutions to your characteristic equation, your M1 and your M2, are not equal to each other, but are both real, then we're going to see exactly what we saw in the starting problem. They're going to be exponentials raised to a power that's given by the zeros of your polynomial equation. So here, since you're going to have 2 of them, you're going to end up with the linear combination of both of them. Here, y is going to equal to some constant times e to the m1x. That's exactly what we saw over here. But since this has got a second solution, that means you're going to have a second element in the fundamental solution set, which makes sense. You have a second degree polynomial, second degree ODE. So that means you're going to have a second element, and so we're going to have just another one added in here as a linear combination with the first. So it's plus c2e to the m2x. Okay. Now, the second case, what if m1 is equal to m2? Now, in this case, they're both real. They're both real solutions. In this case, by reduction of order, we end up getting a second solution. You can actually try this. You can actually, if you take one solution here you get y equals c1e to the m1x. Obviously, you can't come over here and say, okay, that's going to be c2e to the m2x, because those are the same thing. And, well, then they're not linearly independent. If they're equal to each other, they're not linearly independent, and so they can't both be part of the fundamental solution set. But if you actually just take one solution and go through reduction of order the way we did in the last section, you'll get the exact same answer times x. Yeah. So you can actually try that yourself. If you want to practice reduction of order, just take one solution, run it through reduction of order, and you'll get the exact same answer times x. And finally, if they're both complex. Now, if they're both complex, they're not going to equal to each other. If they're complex, they're going to equal to each other's conjugate. In fact, let's write that. If m1 is not equal to m2, our complex conjugates, and we know that whenever they're complex, they have to be conjugates. We get that from the quadratic formula, right? Plus or minus. Our complex conjugates, a plus ib and a minus ib, then your solutions look like this. Y equals c1 e to the ax, where a is the real part of the solutions, times cosine of bx, where b is the imaginary part of the solution. Don't include the I, just the number that's being multiplied times I. Plus, and then the second solution is going to be the same e to the ax, but now sine of bx. You might wonder, why does it look different? Why is it sine and cosine? Why wouldn't we just have something like c1 e to the a plus ibx plus c2 e to the a minus ibx? That's actually true. That is what you get. You say, so then why does it look like this? Why don't we just have that there and that there? You do. But the thing is, whenever you have an exponential with a complex number, you may think back to Cal 2. Think back to Cal 2 when we saw Euler's equation. That was e to the I theta is equal to cosine theta plus I sine theta. Whenever you have an imaginary part in an exponential, it simplifies out into two parts, one with a sine, one with a cosine. I'm not going to go through the actual derivation, but if you do have a plus ib here and a minus ib here, using Euler's equation, you can actually reduce this down, get rid of the imaginary parts, and the expense of getting rid of, there's no more imaginary numbers anywhere in here, is the sine and the cosine are left over. So this is a consequence of the same procedure simplified out with Euler's theorem, with Euler's equation. And it's significantly preferable. We really don't like imaginary numbers in our results if we can help it. Right? So let's go ahead and take a look here at some examples of doing this. And since we've got 3 cases, I'm thinking I want to do 3 examples here. For these, I do strongly suggest that you pause the video as you're going through and actually try it yourself before you see me do it. These are really very accessible as long as you break it down into the 3 cases. Once they're broken down, it's really just algebra and plugging in the solutions of the algebra into the appropriate outcome, into the appropriate case here. All right, so let's give this a try here. We're going to go ahead and solve y double prime minus 36y equals to 0. If you want to try it, go ahead and pause the video, give it a try, and then when you're done, go ahead and unpause the video and we'll try it together. All right, so let's see. So my characteristic equation, this is going to be second derivative, so that's going to be m squared, right? Second derivative, second power, minus 36, no derivative, no power. I can write m to the 0, but I might get confused. I think I'll just not write anything equals 0. Okay, so there's my characteristic equation. Step number 1 done. Step number 2, let me go ahead and solve this. Well, this one's nice and easy. There's a bunch of ways to solve this. Quadratic formula would be overkill. I can't really complete the square because it's already a completed square, right? So here the easiest thing would probably be extraction of the square. Add the 36 to the other side and take the square root. You can also, of course, factor because this is a difference of squares. In fact, let me do it that way. So I get m plus 6 times m minus 6 equals 0, which gives me two solutions, m equals 6 and m2 equals minus 6. All right, positive 6 and negative 6. Okay, so I have two solutions. So I'm done with step number 2. Step number 3, I just have to figure out what cases this fall into. Well, they're both real numbers, but they're not the same. So that's case number 1. So this is case 1. And I'm done. My solution, my general solution, is going to be y equals C1. And remember, you don't need to solve for C1 unless you're looking for a particular solution. General solutions, you just leave C1. E to the 6x plus C2 e to the minus 6x. Oops, that should be an x up here. And that's it. There's your answer. Isn't that nice? You say, well, there's got to be a catch. It's got to get harder. Not really. They can get longer. We might have a 3rd or 4th degree here, but that's not really any different. It's just a little longer. Let's see another one here. Our next example, we're going to go ahead and solve y double prime minus 10y prime plus 25y equals 0. Okay. Once again, I would suggest you try that one. Go ahead and pause the video, give it a try, and once you're done, go ahead and unpause it, and we'll go through it together. Okay, so let's give it a try here. We're going to write the characteristic equation. That's going to be m squared, double prime, second derivative, second power, minus 10m, right, first derivative, first power, plus 25. No derivative, no power, no variable. Okay, well, that can be factored. That's m minus 5 times m minus 5. So if m minus 5 times m minus 5 is 0, we get two solutions. They're just the same solution, right? There's technically two of them, but they're both the same one. So here my m1 equals to my m2. They're both 5. Okay, so what case am I in? Well, now they're both real solutions, but they're the same. So here they're both real, but they're equal to each other. So we're in the second scenario. All right, so now we're done. Our general solution, that's going to be y equals c1 e to the 5x plus c2, and you're going to have the exact same answer, but times x. And again, that's due to reduction of order. You can actually try it. Like if you took e to the 5x as your first solution and ran that through this problem using reduction of order, you'll get x e to the 5x. But you don't need to bother. If you're curious, if you want to see it in action, go ahead and give it a try. Otherwise, yeah, this is it. This is our result. Okay. And let's do one more here. Well, one more second order one. We'll see some. We'll see something bigger here in a moment. But let's do one more that is second order. So we're going to go ahead and solve. Let's do 2y double prime plus 2y prime plus y equals to 0. And again, if you want to give that a try, go ahead and pause the video. I'll put that there. I'll go ahead and pause the video and give it a try. Once you're done, go ahead and unpause the video and we'll go through it together. Okay, so let's give this a try. We're going to write out our characteristic equation. We've got 2m squared plus 2m plus 1 equals 0. Okay. This one looks like it's going to be hard to solve as it is. I'm just going to go ahead and jump to the quadratic formula. Okay. Welcome back to algebra. Here I've got my quadratic formula tells me that m is equal to negative 2 plus or minus the square root of 2 squared minus 4 times 2 times 1 all over double my 2. All right, negative b plus or minus the square root of b squared minus 4ac all over 2a. And now we simplify that down. Oh, let's see. 2 squared is 4. 1 times 2 times 4 is 8. 4 minus 8 is negative 4. So here we get negative 2 plus or minus the root of negative 4 over 4. 2 times 2 is 4 there. The square root of negative 4, that's positive 2, and that's positive 2i and negative 2i. So I've got negative 2 plus or minus 2I over 4. And then here each of these divides. So I get two solutions. I get m is equal to negative 1 over 2 plus or minus 1I over 2. Like that. So here we get two solutions, negative 1 over 2 plus half I, or negative 1 over 2 minus half I. But either way, we have two complex conjugates, not equal, two complex conjugates whose real part is A and whose imaginary part is B. So here we have our A is equal to minus half, and our B is equal to half. All right, don't include the I. Don't include the plus minus, just the number. For A, if it's plus or minus, include the plus or minus. But here, just the number. All right, and now we're done. We can plug everything in. So let's see. I'm going to get my general solution. That's going to be y equals, I've got C1 times e to the, now use your real part as the coefficient of the x in the exponent. So that's going to be minus half x cosine of, now use the imaginary part as the coefficient in the trig function. So that's going to be 1 half x. There's no reason these two have to be the same number, right? That's just how this one worked out, but it could have been minus 1 half and positive 3/8 or whatever. But here it just happened to work out that these look very similar. Plus, and then do the exact same thing, but with sine instead of cosine. So that's going to be C2e to the minus half x sine of half x. And that would be our general solution. Now, with these, we see all three possible cases for a second order problem. But now this technique does sound a little bit limited. After all, you are relegated to looking at only second order homogeneous linear ODEs. Well, so for now, there's nothing we can do about it. It has to be homogeneous, it has to be linear, and it has to be an ordinary differential equation. But the second order part is a little flexible. Right? So let's consider an example of something that's more than just second order. You say, well, how? Our theorem only allows us to look at two solutions. Either they're both real and different, they're both real and the same, or they're both complex. Well, we basically break it into smaller pieces. So consider the following. Let's start with a cubic here. Something like y triple prime, okay? Plus 3y double prime minus 4y equals to 0. Okay, so here this is the third order differential equation, which strictly speaking doesn't fall under our technique, but we can make it fall under our technique as long as we can separate this into smaller cases. So first of all, we're going to begin with our characteristic equation. Since this is a third order differential equation, its characteristic equation will be third degree, so m cubed now. Plus 3m squared, second degree, second derivative, second degree here, and then minus 4, no derivative, no degree, no variable, equals to 0, like that. Okay. All right, so now we have a cubic. Now with cubics, you don't have a quadratic equation to fall back on, but we have other techniques. The simplest technique here is to notice, oh look, 1 is a solution to this. Like, 1 plus 3 is 4 minus 4 is 0. Okay, so 1 is a solution. Okay, sure, but how does that find the rest? After all, this is the third order polynomial. We should have 3 solutions. Well, knowing one solution is very helpful. Here, we know m equals to 1 has to be a solution to this. So, that means m minus 1 is a factor. So right here, I can write m minus 1 times, and now I can just divide. This divided by m minus 1 will give me this right here. To divide this out, you can of course use long division, but since it's a single factor, synthetic division is probably faster. If you don't remember how synthetic division works, the way you do it is you write down the coefficients in order. Don't skip any terms. So here that's third, second. Since there's no first, we're going to fill it in with a 0. So that's going to be 1m cubed, 3m squared. There's no m, and then there's minus 4. And then you're going to divide by, since you're dividing by m minus 1, right here you're going to put 1. You're basically going to put the 0 that you just found earlier. Okay? So here you drop your 1. One time, the pattern is multiply on the outside, add on the inside. The first number you always just drop it straight down. Multiply the outsides, add the insides. Multiply the outsides, add the insides. Multiply the outsides, add the insides. This right here is your remainder, which we know that remainder is going to be 0 because this does divide out evenly. Incidentally, if ever wasn't 0, maybe we made a mistake and that was not a correct factor. But this is 0, so it does divide evenly. And so then these are the coefficients of the other factor. So here that's going to be 1m squared plus 4m plus 4. So if you can find even one solution, where here the number 1 as a solution was pretty obvious. 1 plus 3 is 4, minus 4 is 0. But even that one obvious solution can be helpful because we can divide that out. And now we have a reduced polynomial, reduced in order. But now this is factorable. In fact, I could use the quadratic formula as well, although that would be overkill. This factors out nicely as m plus 2 and m plus 2. But now we have 3 solutions. We have m1 is equal to 1, and of course we had that from earlier. And then over here we have m2 and m3 are both the same thing. Equal to negative 2. Okay, so then how do we set up our general solution? Okay, well basically we're just going to go down the line. We're going to say, okay, I can only deal with 2 solutions at a time using this technique. Okay, so then just go down the line. I know I have 3 of them, but only look at 2 of them at first. Okay, m1 is 1 and m2 is negative 2. Pretend m3 doesn't exist. Just m1 is 1, m2 is negative 2. So for my general solution, I've got y equals c1. I've got e to the 1x, which I'll just write as x. And then for the other one, I've got e to the minus 2x. So plus c2 e to the minus 2x. Okay. So if m3 did not exist, if we just had those 2 solutions, we would have c1 e to the 1x plus c2 e to the minus 2x. And that was case number 1, when they're both different. Okay, but now let's proceed to the next one, m3. You say, well, I can only handle 2 at a time. Okay, but notice that this new one that we have is the same as one of our previous ones. So because it's the same as one of our previous ones, m3 paired with m2 puts us into case number 2, where they're both real and equal. So in that case, we're basically going to pretend m1 doesn't exist, and with just m2 and m3, well, we already have m2 right here, c2 e to the minus 2x. For m3, we're going to get the exact same result, but times an x. So here we're going to say plus c3 e to the minus 2x, but then times an x. And there we go. We basically have our solution done pairwise. Oh, those 2 give me those 2, and then those 2 give me those 2. If all 3 were different, we would just have 3 of these, e to the x, e to the minus 2x, and e to the minus 5x, or whatever it might have been. But since some of them are the same, oh, those pair together to give me a case number 2. And now this gives me a general solution for a 3rd degree homogeneous linear ODE. Just like that. So let's go ahead and try one more here. This will be a little bit bigger. So let's try this one here. Let's do y 5th derivative plus 5 times y 4th derivative minus 2 times y triple prime minus 10y double prime plus y prime plus 5y equals 0. Okay. All right, if you want to give this a try, go ahead and pause the video and give it a try. And then once you're done, go ahead and unpause the video and we'll go through it together. Okay. Okay, so let's take a look here. First of all, we're going to write this out using a characteristic equation. That's going to be m to the power 5 plus 5m to the power 4 minus 2m to the power 3 minus 10m squared plus m to the first power plus 5 equals 0. Okay. So now, to factor this, it would help if I knew a solution. If I knew a single one of these, like, oh, it's obvious that the number 1 is a solution here. Well, I don't know. Maybe something is obvious, maybe something stands out to you, or maybe not. It really is up to each individual person. Some people might look at that and say, oh yeah, obviously this is a solution. Other people look at that and go, I have no idea. Thankfully, we do have a more methodic way of going about it. If there isn't something that if something does stand out to you, please go ahead and do that. But if nothing is standing out to you, you can try what's called the rational zeros test. This is something you learn all the way back in algebra. You may or may not remember it, but here, let's go ahead and remind ourselves. This is what's called the rational zeros test. All right. This test will not give us any solutions that are irrational. So like if square root of 2 is a solution, you won't find that. It also won't give us any imaginary solutions. If 1 plus I is a solution, we won't find that either. But if any whole number or fraction is a 0 of this, we'll find it using this technique. Here's how it works. You're going to take the constant all the way at the end and find its factors. Okay, so factors of 5. Divided by, you're going to take the lead coefficient. So you're going to take this 5 at the end, and you're going to take this 1 at the beginning. And depending on what the numbers are, this might take a long time. If this is, I don't know, 120 and this was 45, okay, there's lots of factors of those, so this takes a while. But of course, we're not interested in making you spend forever on this, just long enough to get the problem done. So here, the factors of 5 are just 1 and 5. And I guess minus 1 and minus 5 as well. The factors of 1 are just 1 and minus 1. So now what you do is you make fractions out of these numbers. Every fraction you can. So 1 over 1 is 1. 5 over 1 is 5. Negative 1 over 1 is negative 1. Negative 5 over 1 is negative 5. 1 over negative 1 is negative 1, which we already have that. 5 over negative 1 is negative 5. We already have that. Negative 1 over negative 1 is positive 1. I've already got that. And negative 5 over negative 1 is positive 5. And I've already got that. So these right here represent every possible rational number that could be a 0 of this. Now, maybe they all work, or maybe only some of them work, but whatever rational zeros we have will be among this list. So what we do now is we use either long division or synthetic division. Again, synthetic division is usually easier for small problems like this. So here we go. 1, 5, minus 2, minus 10, 1, and 5. And I didn't skip any, right? Power 5, 4, 3, 2, 1, 0. Nope, nothing was skipped. So now we're going to divide synthetically by, you just pick one. If you're feeling lucky, go ahead and pick one. So I'll go with, I don't know, let's go with 5. Let's do with 5. Okay, so drop your 1. This may or may not work. The way you'll know is if there's no remainder. If there's no remainder, then you divide it evenly, and that's a correct factor. If there is any remainder at all, then that's the wrong one, so you'll try a different one. So drop your 1. 5 times 1 is 5. Add on the inside. 5 plus 5 is 10. 5 times 10 is 50. Add those is 48. 5 times 48, that's 240. Add those on the inside, that's 230. 5 times 230, yeah, that's not going to work. These numbers are going to get too big, aren't they? So let's see, that's going to be 15, that's going to be 1150, plus 1 is 1151. And then multiply that by 5, that'll give me 5. That'll give me 5, carry my 2. That'll be 5755. And so that is definitely not a remainder of a 0. Okay, so that number does not work. Okay, so if that works, cool. If not, well, then that doesn't work. So let's try a different one. I got 1, 5, minus 2, minus 10, 1, and 5. Let me try -5 this time. I noticed that the number got really, really big, so maybe a negative will help keep that balanced a little bit. We'll see. So drop your 1. -5 times 1 is -5. Add those as 0. Okay, we're off to a good start. The numbers are not getting too big right away. -5 times 0 is still 0. Add those as -2. -5 times -2 is +10. Add those gives you 0. Yeah, this is going to work. -5 times 0 is 0. Add those together as 1. And then -5 times 1 is -5. Remainder is 0. Okay? So this does tell us that our polynomial is going to break apart as, so -5 is one of our solutions, which means m plus 5 is one of our factors. Our other factor will be, let's see, that's constant, first power, second power, third power, fourth power. So m to the power 4 minus 2m to the power 2 plus 1. You say, do I have to do that again? You might. If you're not sure what to do next, you could do this a second time to see if you can find another 0. But a lot of the times, once you factor out even one factor, what's left will be simplified enough that maybe you can factor this a different way, something that doesn't require quite so much arithmetic and trial and error. This is quadratic in form. I can factor this as m squared minus 1 times m squared minus 1. All right, because that's m to the 4th minus m squared minus another m squared is minus 2m squared, and then minus 1 times minus 1 is 1. But now these are both differences of squares, so I factor as m plus 5, m plus 1, m minus 1, and over here, m plus 1 and m minus 1. So we have 5 solutions, but 2 of them are doubled up, or rather 2 pairs of them are doubled up. So here I've got m1 is equal to -5, m2 equals m3, that's equal to, let's see, I've got, what, 1? I'll do them in the order that I have them written, so -1. And then m4 and m5 are both +1. Okay? So from here, we can now break this into cases and get our general solution. Okay? So our general solution, y equals, okay, so starting just from the top, forget about the fact that there's 5 solutions, just the first 2. Okay, well, those are different. -5 and -1. So simple enough. C1 e to the minus 5x plus C2 e to the minus 1x. Okay. All right, but now let's take our next 0. Oh, and that one is just like one of the previous ones. Okay, so because it's just like one of the previous ones, we're in case number 2. And so you're going to have to take the exact same answer you just got for this one, but times x. So it's going to be plus C3 x e to the minus x. Okay. So now so that was 1 and 2 gave me the first 2, and then 2 and 3 gave me the next set. But now let's go to 3 and 4. Okay, well 3 and 4 are totally different. -1 and +1. Oh, so since it's different, I'm just going to use that 1 as the coefficient in my power. So the next one will be C4 e to the 1x. Okay, but now let's look at C4 and C5. Oh, C4 and C5 are the same. Oh, okay. So here I've got the same answer I got for C4, but times an x. So that'll be plus C5 x e to the x. And this big-looking expression, this big-looking equation, would be the general solution to my problem, which makes us happy. All right, so that is it for that problem. That is it for this section. If anybody has any questions, comments, or problems, please reach out. Let me know. Otherwise, I hope you all have a nice day.